Okay, it's a pleasure to have Professor Çağatay Başdoğan as part of ROMER Talks in season 2. I think it's episode 6, I guess. Let me just briefly read his bio, and I like his bio because I think it's the way it should be. It's not just a timeline, but he kind of mixed up things such that the important parts go at the front and at the back. So Professor Başdoğan is a member of faculty in College of Engineering at Koç University since 2002, so it's been 20 years. And before joining, he was a senior member of technical staff at Information and Computer Science Division of NASA's JPL lab of Caltech from 1999 to 2002. At JPL, he worked on 3D reconstruction of Martian models from stereo images captured by rover and their haptic visualization on Earth. He moved to JPL from MIT, where he was a research scientist and principal investigator at MIT Research Lab of Electronics and a member of MIT Touch Lab from 96 to 99. At MIT, he was involved in the development of algorithms that enable a user to touch and feel virtual objects through a haptic device. He received his PhD degree from Southern Methodist University in '94 and worked on medical simulation and robotics from Muscular Graphics Inc. At Northwestern University Research Park for 2 years before moving to MIT. He conducts research and development in the areas of human-machine interfaces, control systems, robotics, mechatronics, human-robot interaction, biomechanics, computer graphics, and virtual reality technology. In particular, he is known for his work in the area of human and machine haptics, with applications to medical robotics and simulation, robotic path planning, micro and nano optical telemanipulation, human-robot interaction, molecular docking, information visualization, and human perception and cognition. In addition to serving in the program and organizational committees of several conferences and journals, he also chaired the IEEE World Haptic Conference in 2011. So without further ado, I would like to leave the floor to him to talk about his basically recent work on adaptive admittance controller for collaborative drilling with a robot based on subtask classification via deep learning. Floor is yours.
Thank you, Erol. Thank you very much for inviting me, and I see that my bio was a little long. They asked me to send a bio, but maybe I should have sent a shorter one. Yeah, I have been in States for almost 12 years and then moved back to Turkey in 2002. And I have been with the Koç University for 20 years. And today I'm going to talk about, I changed my title a little bit to emphasize physical human-robot interaction, but I'm going to discuss this adaptive admittance controller, and I will give you more details about the work that we've been doing. Thank you for inviting me, first of all. It's a pleasure to give a talk. I am excited about the developments in ROMER. I'm very happy to see more and more people are getting into the robotics, AI, and that's very good. And you are one of the pioneers in this area, which is great. So what we do in robotics and mechatronics laboratory is we conduct research. I want to give a very brief information about what we do. Like, we conduct research in the area of man-machine interfaces, in particular haptics. I mean, we're known in the area of haptics particularly. And as a research laboratory, we are interested in human haptics, how people touch and sense objects, rigid objects, soft objects, how we can transfer that information to machines, including robots or computer interfaces. And more, we are interested in interactions between the machines and humans through the sense of touch. So we're interested in haptic communications, like verbal communication involves words, sentences, and haptic communication naturally involves forces, vibrations, and things like that. Currently, I have 12 students in the lab, 6 PhDs and 6 master students, and research, my current research is focused on two areas. One is in the area of surface haptics, and I will give you a very brief information. So for those of you who are interested, you can contact me for more information. In the case of surface haptics, we are being able to control friction on the surfaces of touch surfaces of mobile devices. So we can really control the friction on the surface of your cell phone or tablet. This has a lot of interesting applications, including, I'll give you only one of them. Online shopping is one interesting application. For example, in the future, when you buy a sweater, you're not just going to choose the size or the color of it, but maybe you will touch, feel, and make a decision based on the fabric as well. So this kind of interface enables you to do that. So we have like 4 or 5 students working in this area. And the other group is working in the area of physical human-robot interaction. Again, I want to emphasize human-robot interaction is a large area in nowadays, but our focus is physical, and that's where the haptics comes into business, right? When you interact physically with somebody, of course, there is exchange of forces. So our research is focused on this physical human-robot interaction. So this means, and also within the domain of physical robot interaction, I want to further emphasize that the human and robot are in continuous contact in our scenarios, okay? There's also the intermediate contact cases where human does some work and then robot does the other part of the work. But our focus is more on continuous contact. Okay, so what will I talk about? I will make a quick introduction to physical human-robot interaction, but I'm assuming that most of the listeners are familiar with that concept. Maybe I can go fast this part. And then I'm going to talk about the application we develop in our laboratory. It's a collaborative drilling. This is a drilling done with human and robot together. And I'm going to talk about the adaptive admittance control architecture we developed so that we can adaptively change the parameters of the controller during the task in real time. And I will also talk about the subtask classification. So we change the admittance control parameters based on the subtask classification. So we classify 3 subtasks like idle, driving, or free motion, and also the contact. These are typically the subtasks that you encounter when you do something with the robot, especially in small batch manufacturing scenarios, which I will talk about it. Then I will talk about the experiments that we have done and discuss the results of the experiments afterwards. Okay, so why physical human-robot interaction is important? Well, I mean, we know robots are very good at positioning objects. They can repeatedly do this. They are rigid and I mean, in a sense that they are faster than us, obviously, right? And these are really good, but what's missing with the robots is still missing is intelligence and awareness. Like, for example, you can see the back on the back of the screen, like you can see the bookshelf. Like if I want to grab a book in here, I don't know where's my books, but like if I want to grab a book and I want to put it into the shelf, I need to find an open space on the shelf and then place the book, which I can do it very easily. But for a robot, this is still a very difficult task. Like you need cameras. The cameras has to scan the shelf and decide on how much gap is in there. Is it sufficient to insert the book and things like that? But like, imagine that I am doing this operation with a robot, right? I'm bringing robot close to the empty space, and then final adjustment is done by the robot itself. So this is the type of collaboration that we are talking about, right? Human utilizes its intelligence, finding the empty space on the shelf, and robot is utilizing its precision in placing, positioning that book to the shelf, right? So this is the type of environment architecture that we're talking about. So if we can implement this architecture, what we call it physical human-robot interaction, then we can do the tasks probably faster. It could be more ergonomic and more efficient in terms of the task performance. And PHRI has many applications. Again, I'm going to assume that this audience is already familiar with these concepts, but I will briefly mention some of the applications. There are interesting applications in the area of manufacturing, in the area of medicine and rehabilitation. For example, you can assume that like in here, robot and human are transporting a heavy object, right? In this scenario, robot is handling the weight of the object, while the human is giving the direction, providing the direction, so that human doesn't have to lift the heavy object, right? Or another scenario, like again in the manufacturing environment, like where human and robot are doing a welding operation. In the case of welding, two parts are put together and then you put a weld in between them, you do welding between them, and then this requires some precision, right? The human can bring again the robot very close to the operating area, and then the robot can do the task which may require a good positioning of the welding beam. Again, you can extend these ideas, these concepts to rehabilitation, where the human and robot are working together, and robot helping as needed, like especially in rehabilitation area now. In nowadays, the paradigm is assist as needed, which means the any exoskeleton type of device is helping you when you need assistance. Otherwise, human is doing the task. This paradigm is important because you don't want everything to be done by the robot or the exoskeleton device. That's not gonna rehabilitate the patient. Okay, so I mean, I hope that this scenario motivates. And in our application, we focused on the drilling. It's a manufacturing application. And I like to tell you why we focused on the manufacturing, because there are, oops, the light is off. Sorry about that. The lights are going off in my office. So I'm going to do this kind of strange movements during my talk. Excuse me for that. So we focused on the small batch manufacturing operations. These are the operations that you do. These are the tasks that you do, not on the assembly line, right? Either because it is not cost effective, or it's not practical, or it may not be even doable. Like if you're working flexible parts, if you're working on curved parts, so that which they need to be fixated. So the assembly line may not be an option. So you have to do this kind of operations out of the assembly line. So this operations I'm talking is like you have seen already one of the examples: welding, soldering, polishing, drilling, and they all involve some type of contact with the environment. Okay, and then we picked one of them. We picked the drilling because we were funded by Turkish Science Foundation, and one of our collaborators was a company which was developing machinery for woodworking, and they were interested in integrating robots to their systems. And while discussing with the company, we came up with some interesting applications, which I'm going to talk about in here. So in the scenario that I'm discussing here, you can see the human and robot are working together to open a hole on a workpiece. This workpiece is, you can see in here, is a wooden workpiece, and it's a flat surface in here. And the goal in here is human and robot are working together, and robot is helping the human to do this task more accurately and precisely. So there is a location is given on the wooden piece, and the depth, drill depth is given. And you can see the components of the system. We have this cobot, collaborative robot, KUKA, LBR, EVA robot, This is the collaborator robot that we use. You can see the, I hope you can follow my cursor. Can you follow my cursor during my talk? Yes?
Yes, we can,
Okay,
we
great.
can.
So you can see the drill that we attached to the end effector. And we also attach two force sensors, like one force sensor measures the interactions between the drill bit and the workpiece, and the other force sensor measures the force applied by the human through the handle. So you can see human is holding the handle and pushing the drill towards the drill bit. Okay. So, and also there's the slider mechanism moves the wood piece moves perpendicular to this page. And so you can open holes in different locations on the wood workpiece, okay? We also have this AR interface. It's a HoloLens. It provides information about the steps of the operation to the user, and also it helps with the drill depth. Okay, so it provides information how much you penetrated into the workpiece. So let's say you want to penetrate 5 millimeters, so it helps you to stop at the desired depth. So what is the idea in here? So the idea in here is like you want to pull the robot close to the workpiece, right? And during that operation, you want the robot to be compliant. In other words, you want the robot to show very little resistance to you, as if that you're pulling the arm of your friend, bringing close to the workspace, okay? But during the drilling operation, we want the robot to be rigid, okay? And so that means two different like control parameters. And I'm going to talk about more on this in the upcoming slides, but I want you to get the idea, like during the free motion or during the driving phase, you want the robot to be compliant, but when you make a contact with the workpiece, you want the robot to be rigid, because if you still go with the compliant robot, which happened to us, like drill bit can break very easily, okay? You want your robot to be highly rigid. This also is important in terms of the safety to the user. All right, so let me move on. And so this was how we started the work, like drilling on wooden workpieces. You may say, what's the idea in here? Why is it so interesting? Like our partner said that the real challenge is to drill something on a curved surface. Okay, because opening a hole, if you have a drill in your hand, opening a hole on a curved surface with a certain desired angle is very, very challenging, almost impossible. We tried many times in the lab, actually. So if I tell you, for example, if I mark one of these points that you can see on the screen, like 1, 2, 3, so these are the drilling points. And if I say, like, go to the point number 1 and open a hole with a angle of 30 degrees to the surface, that's not possible. That's very hard to maintain that angle. So we start thinking about how we can get the help from the AR interface and from the robot to do such a task, okay? So the idea in here is human selects the drill target, the location. Let's say one of these points that you see on the screen, so it marks the point. And then it brings the drill bit close to that point and roughly aligns the drill angle using the HoloLens interface. You can see on the lower right, you can see the HoloLens interface. What you see is you see a white color arrow on superimposed on point 1. You see a white color arrow and you see a red circle, right? So red circle represents the drill point and white color arrow represents the drilling angle. So you see this information superimposed on the real wooden workpiece. And you bring your robot close to that position and roughly align it, and you let the robot do the rest of the work for perfect alignment. So robot takes over and makes the perfect alignment. And then again, human user performs the actual drilling, But what's the benefit in here is like we lock the direction, we lock the direction of movement along the angle of drill. Okay, along the drilling angle, we lock the movement so that all you have to do is just push the drill towards the target, nothing else. It's not going to move in any other direction other than the direction of the drilling angle. So let me show you, we presented this work very recently in IROS conference in Tokyo, and people enjoy it. This is a very shorter version. We had a longer version of the video, but since I have a limited time, I'm including a shorter version of the video and you will see the idea. It's pretty simple actually. Let me play it. I hope you can see it. So the user holding it and moving to the drilling target, let's say number 1, and bringing sufficiently close, aligning roughly. And then now you will see that the robot is taking over, making perfect alignment, accurate alignment. And now the robot is ready. You can push the robot. It's not going to move in any other direction than the drilling direction. So you can make the hole and move to the second point or third point. Here, user is deciding on the drilling point. User is deciding the drilling angle. And you can see this is the idea behind the flexible manufacturing, flexible automation, flexible manufacturing. So even we have in the extended video, you see that the user can hold the workpiece and still this operation works. Like it doesn't have to be fixated on the table because we're tracking the movements of the workpiece using Aruka markers attached to the workpiece that you can see in here. So we know its position and orientation so that you can even like make holes with desired angles while you're holding the workpiece by yourself. I hope you get the idea, and you know, don't hesitate to interrupt me anytime you want. If you have any questions, I'm gonna move on otherwise. Okay, you can ask your questions also at the end of the talk. So to be able to implement such a thing, you need something called interaction controller. This is something different than trajectory controller. Like I'm sure that you are familiar with this PID controller, right? PID controller is a typical trajectory controller. So you have some desired trajectory or desired position. So a PID control enables the robot to come there. But in the case of human, especially physical human-robot interaction, there is no such a thing because human is pushing the robot and robot has to move somehow, right? So there is no such a thing like a desired trajectory. So what you have to use under that circumstances, you have to use something called interaction controller. So this regulates the interaction between the human and robot. And typically there are two types of interaction controllers. One is admittance controller. The other one is called impedance controller. In the case of admittance controller, interaction force, remember there are two force sensors. One is measuring the interaction force. In other words, the interaction between the drill bit and the surface. So interaction force is inputted to the admittance controller. You can see it's not very sophisticated. It's something simple. 1 divided by mass times S is the Laplace variable and B is the admittance damping. In here, M is the admittance mass, B is the admittance damping. So it's a very simple controller. So this where you input the interaction force and it generates some reference velocity or desired velocity, and the internal controller of the robot follows that desired reference velocity. Okay, and so we extended this concept. So this is a typical admittance controller, or it's called actually officially called integer order admittance controller. Okay, we extended this concept to fractional order admittance controller. So you can see the main difference between integer and fractional order, the power above the S term, Laplace term, there is something called alpha. So this is the fractional order. So that's the main difference. So, I mean, in a simple sense, it adds one more parameter to your controller to regulate the interactions. What is this fractional? What's the idea behind the fractional control, fractional order? Let me give you a very simple example. Let's say you have a position signal. If you take the first derivative of that position signal, you get velocity, right? If you take fractional order derivative, let's say 0.6, right? X to the power 0.6. So you get somewhere between position and velocity. So it's not exactly position, it's not exactly velocity. And this enables a larger bandwidth for your system. And also, in a simple sense, it adds another parameter that you can utilize for regulating the interactions between human and robot. So we have some detailed publications on that topic. I'm not going to go through the details, but more information can be found in those publications. So the idea is interaction force. You can see if you look at it, the simplified control diagram, the interaction force that you're measuring goes through some low pass filter to eliminate the noise in the measured signal and input it to the admittance controller, and the admittance controller generates some reference velocity, right? And then that is supplied to the robot, and the internal controller, which is the PD controller, internal controller of the robot aims to follow that desired trajectory, and that loop goes on. Okay, so that's this is actually a simplified version of this loop. More details available in our publications, but I'm hoping that now you can, with this slide, now you can differentiate the difference between trajectory control and interaction control, and I can move on that. All right, so what's the idea? So we focus on adapting this admittance controller. Adapting means we want to adapt the parameters of this controller, right? Remember, like in the case of integer order controller, there are two parameters: admittance mass, admittance damping. In the case of fractional order controllers, I have three parameters that I can control or play with it: admittance mass, this fractional coefficient, alpha, and then the admittance damping. So we said that, okay, if we change, we can define the task like any small batch task, such as drilling, into three phases. So you can extend this concept to the other tasks easily, or you can increase the number of subtasks. So we have, in our scenario, we have subtasks. We simplify it. Like we said, okay, there is an ideal phase, is the start of the task. There is driving phase, meaning that human is pushing the drill and the robot towards the target. So we call that one is a free motion or driving phase. And then there is a contact. So you can generalize this to many other small batch operations. Think about it, like welding, same, cutting is same, polishing, soldering. In all of them involves this ideal phase where it remarks the beginning of the task, and then you have a driving subtask like free motion, no contact with anything, and then you have the contact. Okay, so our idea is really simple: using signals, the measured signals like force signals and also velocity, can we detect these subtasks using machine learning techniques. So once we detect the subtask, which phase that you are in, then I can adapt the control parameters of the admittance controller. So in other words, like during, for example, ideal phase, I can start with some medium amount of damping, so that when I hold the handle, the whole structure doesn't shake. And then during driving, I can have a very low damping, so that the robot becomes compliant and follows my motion very easily. But during the contact or during the actual drilling, I can make the robot rigid by increasing the damping, so that I can dampen the oscillations, vibrations during the contact. Okay, so that's the main idea in here. And you can see the signals recorded during one trial. In here, we focused on these 3 signals. You see like red colored one represents the velocity of the end effector, or you can say that velocity of the drill bit. Okay, and dash green one represents the interaction force. This is the force between the drill bit and the workpiece. And the dash blue colored one is the force applied by the human. So this is the typical, these are the typical profiles you can see, like during the driving, of course, you accelerate and then decelerate, and then you make, at some point, you make the contact. And when the contact happens, you can see that human force gets separated. They are, during driving phase, they are same, human force and interaction force, because there is no contact. There is no reason why they should be different. But at the contact, human is pushing the drill bit into the workpiece to open a hole, so the human force increases and the interaction force is decreasing. So we use these signals to be able to detect the subtasks, idle, driving, and contact. All right, so once you detect the subtask, once you know at what phase or what subtask that you are in during the task, then you can adapt the control parameters. So we do the adaptation of damping. We don't touch the mass. We play with the damping, which kind of like more intuitive, like if you think about it. So you display some nominal amount of damping during the idle phase. So when I go and make a contact, when I go and hold the handle, it doesn't shake. And then after like holding the handle, as I push it towards the workpiece, then I display, like I set the damping to a low value so that the robot becomes compliant. It shows very little resistance to my movement. And then when I detect the contact phase, then I am increasing the damping to make the system more stable, okay? Like in our articles, we like talk about this trade-off between what we call it transparency, like minimal resistance to human behavior, versus stability, which is important during the contact phase. So transparency is important during the driving phase, while the stability and safety of human is important during the contact phase. And that transitions have to be done smoothly, right? It cannot be abrupt transitions of the damping, admittance damping value. So we just like interpolate the values by giving some time interval. We are interpolating the values, trying to make the passage from one phase to another one. We try to make it smoother. So we not only play with the damping, we also play with the this fractional order coefficient, because in our earlier theoretical studies, we observed that like reducing the fractional order coefficient improves the stability of the system. So we use this theoretical knowledge in this experimental study. So we reduced the fractional coefficient from 1 to somewhere around 0.8 during the contact phase to make the system even more stable during the contact phase. Let me stop very briefly. If you have any questions, feel free to ask in here. Otherwise, I will move on.
I think you can just go on.
Okay,
Thank you.
sure. So these are the parameters we use. I don't think they are very important. I mean, like for the presentation purposes, but these parameters are selected based on some high theoretical analysis, which were reported in our journal papers, conference papers, that you can go and look at it. So we didn't randomly select these parameters. We selected such that they are in the stable range, and we use like stability maps, transparency maps. We did some dynamical analysis of the robot and all those kind of things. We put them together and we selected some range of values for each of those parameters. All right, so like how will I detect the subtask? Like, so the idea in here using machine learning, deep learning, rather than rule-based techniques, So you can think of like either I can use a rule-based techniques, I can somehow define some rules based on the recorded signals of velocity, human force, and interaction force, or I can use some type of machine or deep learning techniques. We prefer the machine learning or deep learning techniques because rules are, you can define rules, but as the users change, as the environment change, what I mean like by the environment, like let's say the object that you're drilling, like workpiece, it could be different, like it could be wood or it could be metal, so the forces will be different. So defining some thresholds, some rules are not going to be that easy. So that's why we prefer the deep or machine learning techniques to identify or to classify these subtasks. All right, so this is the real control and machine learning architecture in here. I mean, I don't want you to get overwhelmed, but you can see like velocity signal that we are recording or we're obtaining from the robot. This is the actual velocity, which is the velocity of the drill bit, because drill itself is rigidly connected to the end effector of the robot. So this is the drill bit velocity that is fed to the artificial neural network. The human force, you can see, is fed to the ANN, and interaction force signal also fed to the ANN. So remember again, like we are measuring human force, interaction force using force sensors. We are also measuring the velocity using a sensor inside the robot at the end effector and feeding that signals to the artificial neural network. And then that generates a label, like, or that generates a class. Like it says either you are in idle stage or free stage, like which is driving, or the contact stage. And then we have like a post-processor. I mean, this is something interesting because this kind of post-processor is required in our case, in physical human-robot interaction. Because why? Because ANN will never tell you with 100% accuracy which class you are in. It's impossible, right? Like, you are CS people, you know better than I do that. And none of the machine learning algorithms will return 100% accuracy. So it may return, let's say, in many of the machine learning applications, and 90%, 97%, 98%, these are very good values, right? But in the case of like this physical human robot interaction, which involves contact with the environment, that 2% is important. Why? Because if you are changing the, let's say, damping, like you are thinking that you are in the contact phase and you change the damping to a high value, in the next second, your algorithm says, oh, no, you were not in the contact phase. You are now actually in the driving phase. It's going to like drop the damping again. So this kind of oscillations, fluctuations are highly harmful for the robot and also for the user. Remember, like this is a coupled system. This is why I'm emphasizing over and over physical human-robot interaction. In other words, the dynamics of the human affecting the robot, robot's dynamics affecting the human. So anything going unstable with the environment will definitely affect the human and robot altogether. And this is not acceptable, or this is not desirable, actually. So that's why we're doing some type of post-processing. So we're looking at these labels, and then we have some kind of filtering process. We're accumulating them in the buffer, and then using a filter, we decide on what the actual label is. So that's what the post-processor is doing. Once you know the label, then we make the adaptation of, you can see that adaptation mechanism adapts the admittance damping and the fractional order coefficient. All right, so you can see the signals that we have. Oh, again, the light is go off. I'm sorry. So you can see the phases, idle, driving, contact, and you can see like dash line damping represents the adaptation of the damping. Black dash line is representing adaptation of damping. This red and blue colored lines are the detected labels. Like this trial is going from 0 to 11 seconds. So the first 2 seconds is ideal, then 2 to somewhere around 6 seconds. I'm detecting driving or free motion, and then I'm detecting contact from somewhere around 5.5 to 11 seconds. And you can see the corresponding signals, and you can see like during the contact, interaction force is oscillating, human is pushing, penetrating into the wooden piece or the workpiece. So the force is increasing, blue one, human force is increasing, while the interaction force is fluctuating due to the interaction between the drill bit and the workpiece. All right, so our deep learning model, like we use a deep learning model. We wanted to keep our model really simple because another important issue in physical human robot interaction that you have to run this control loop at a very fast rate, okay? Anything involves contact has to be running at very high rate. So for example, in our scenario, like this loop that I show you, the control loop is running around 500 hertz. So this leaves us 2 milliseconds to make a decision. And that's why the footprint of our deep learning model has to be really small, okay? So again, you can see like we are feeding velocity, like array of velocities, 60 data points for each signal. So 60 velocity values, 60 interaction force values, and 60 human force values. And then we have 5 little hidden layers. And then, you know, these are pretty standard, so nothing is earth-shaking or new in here. But my main point is that, you know, the model has to be relatively small to be executed in real time. So the output of the model is idle, free, meaning like driving and the contact. All right, so we did the training and testing with different workpieces, for example, to demonstrate the idea. In the case of training, you see like if you focus on this, we use plywood, which is kind of like hard material compared to the cardboard, which is very soft, that we use during the testing experiment. So the forces, contact forces, interaction forces were significantly different from each other. We even changed the drill that we use to see the effect of it. Like in one of them during training experiments, you can see that the drill RPM was slow, 2000 revolutions per minute. But in the case of testing experiments, which we use a different drill, like having a higher power, higher rotational speed, right? We use even like different admittance parameter values during training and testing. I mean, like range of values, of course. You can see the values in here. So, I mean, we tried to really break the system as much as possible. And we tested 3 different controllers, okay? C1 is a fixed integer order controller. So admittance, mass, and damping are constant. So no adaptation. So C1, there is no adaptation in C1. In C2, we only adapt the damping. So it's an adaptive integer order admittance controller. In C3, we adapt damping and then fractional order parameter. Especially we want to see, like in our theoretical analysis, I told you earlier that in our papers in IEEE robotics, we like reported that like by reducing alpha, you get a larger bandwidth and you get a more stable system during contact. Okay, so we want to test this theoretical analysis in here with the real system. So that's why we adapted this fractional order coefficient. So that's how C3 is different than C2, okay? So C2 and C3 controllers are adaptive controllers, but C1 is really a fixed controller, no adaptation. And number of subjects and the subjects itself are different again. I want to emphasize all of these are important. So these 7 subjects in the training are completely different than the 12 subjects in testing. I want to mention those as well. All right, so you can see the accuracy. It's pretty good because it's relatively simple subtask classification task. I mean, like it's relatively simple task for subtask classification algorithm. So you see the accuracies are pretty good, like 98%. And you see the confusion matrix in here, like misclassified. Some classes are misclassified, but not that significant, okay. Also, so once we see that, like the subtask idea, subtask classification idea is working, we wanted to see the differences between these controllers, C1, C2, C3. So to be able to compare these controllers, we wanted to define some metrics, okay, performance metrics. So these are the performance metrics we define. We measure the average human force during driving phase. So we wanted to, we measure the average velocity during the driving phase. We measure the effort during driving phase, because remember, like the goal is to, by doing adaptation, reduce the effort during driving, like making it movement is easy, less resistance from robot during the driving phase. And also during contact, we want less oscillations, more stability. And one way to quantify the stability is contact oscillations between the drill bit and the workpiece, okay? So we measure the amplitude oscillations during the contact phase. So these are our performance metrics. So in terms of the performance metrics, these are our results. You see the results on the screen. So C1, C2, C3 are the controllers that we want to compare, right? C1 is, there's no adaptation. C2 and C3, there is an adaptation of the control parameters. C2, there is only one parameter is adapted. In C3, we adapt the two parameters, especially the fractional order parameter, to get more stable results. And you can immediately see, if you look at it, the graph on the right, you can immediately see that contact oscillations are less in the case of C3. So really this introduction of this alpha parameter, as we observed in our theoretical analysis, improves the stability, reduces the oscillations, okay? So in terms of effort, human effort, like the I want to mention in here that the stars at the top of the bars are showing statistically significant differences. Like, so let's say we are looking at the effort, like the third graph from the left. If you look at it, the third graph from the left, effort made by the human. So during the driving phase, human puts a lot of effort under fixed admittance, and it puts a less effort under adaptive admittance. This is something we were expecting. And you can see, like red bar, red column is different than green, and red column also is different, statistically different than blue one, but there is no difference between green and red. So in terms of performance, C2 is kind of like similar to the performance obtained in C3. Okay. So in general, what we can say from here, if we summarize it, I mean, what we can say in here is we are obtaining less effort in driving phase if we use an adaptive controller. And if we use a fractional order controller compared to integer order adaptive controller, we also get a more stable interactions between the drill bit and the workpiece itself. And these are the time plots for all subjects. The bold curves are the average values, and you can see the confidence intervals around the solid lines. So that's representing the whole data itself. And even in here, you can see the velocity in C1, this is the fixed controller, is lower compared to the velocity obtained with C2 and C3. So they can drive faster because the damping is adapted. You get a low damping during driving under adaptive controllers. And also, you can see the human force also is reduced because you can more easily move the robot during the driving phase. All right, so the conclusion is, I mean, this idea of subtask classification for adaptation of control parameters, I think is a valid idea. It can be extended to other small batch operations that I mentioned earlier, like welding, cutting, soldering, polishing. It can be extended to that because they also involve, those tasks also involve those three phases, those three subtasks: idle, driving or free motion, and contact. Adaptation is good in terms of reducing human effort and also improving the stability during the contact. And looks like fractional order adaptive controller is a bit better than integer order adaptive controller, especially the contact phase of the task. All right, so I'd like to thank you for attending this seminar, and let me put the last slide, so feel free to ask your questions, please.